Hello, welcome back to our sixth lecture on technologies of herbal concentration and extraction. And today we're going to be talking more about chemistry. The goal of today is how do we determine how much of a change happens during some sort of chemical or physical transformation of plant materials. I want you, by the end of today, to understand basic reactions and their notations, be able to calculate equilibrium extents, evaluate how temperature alters equilibrium, and understand how molecular structures relate to polarity, volatility, and thus these equilibrium extents. If you remember from last time, we had discussed things about functional groups and fragility, where we had looked at hydrocarbons and said that these are generally highly stable, while things like aldehydes are generally fragile and highly reactive. Let's start putting some numbers and something a little bit, um, you know, more behind that so that we can characterize this a little bit better. So what does fragile mean? So in this terms, fragile is a way that we're going to describe something that is unstable molecule, right? It easily reacts or transforms into a different type of chemical structure, right? And so this leads to the question of what is a chemical reaction, right? And so for us, we're going to define a chemical reaction as a change in the arrangement of intramolecular bonds. So in our class, we have a few different possible examples. The first being oxidation reactions. So in general, these are reactions that are undesirable. So we can take the nice citrusy notes when it's exposed to oxygen. Um, these can form limonene hydroperoxides. We can undergo hydrolysis, where we take our um, linylyl acetate, so one of the key compounds from lavender. It reacts with water to form linalool and acetic acid, so this would give it vinegary notes. We can have thermal degradation just by heating up citral. It can form p-cytamine and other terpenes. And then we can have reactions that are um, decarboxylation. So in general, this is a desirable reaction. So we have THCA, we heat it up and it forms THC and CO2, right? So all of these are undergoing some sort of chemical change. We can write our chemical reactions in this form where we have a reactant. So what we start with, an arrow saying that there's a transformation that's happening, and then what it goes to, what it reacts to. And so we can have different numbers of reactants and products. So here's a unimolecular reaction. So A goes to B. We can also have A goes to B and C, right? So this would maybe be a decomposition reaction. We could have two reactions, A plus B goes to C, right? So here B and A are reactants, C is the product. And then we could have, something like this where we have A and B goes to C and D. So not only can we have these reactions uh, move forward, but we could have two of the same species. So two A's maybe react to form B and C. So this number out in front of the species is called the stoichiometry, and it's going to tell us how much of A, in this case, because there's two Z's in front of the A, how much of A is needed, how many molecules are needed in order for the reaction to occur. Often we think of life in terms of mass, how much stuff weighs. But this is not how chemical reactions take place, right? The chemical reactions are actually taking place in terms of the molecules themselves. So we need to convert these masses, because that's what's measurable, into the number of molecules. And the units that we use in counting the number of molecules is called a mole. Uh, MOLE or abbreviated MOL. And there are um, an Avogadro's number of molecules in a mole. So this is 6.02 times 10 to the 23rd. So we can convert how many how many molecules are in a mole based on their weight using the molecular weight. And so this molecular weight tells us how much mass is there per molecule. Right? And so this molecular weight is in terms of grams per mole. And the molecular weight is the sum of the number of each constituent, right? So if we have one carbon, N would be one. If we had five carbons, N would be, for carbon would be five. And the mass of that species is found on the periodic table shown here and right beneath it, but sometimes it's shown in the upper right-hand corner. So carbon has a molecular weight of 12.01, usually just round it to 12. So with this, we can convert uh, masses of material into the number of molecules. So for example, if we had 10 grams of linalool, how many molecules do we have? Right? How many moles do we have? Right, so we first need to calculate the molecular weight. Here is the structure of linalool. And then its formula, if you remember, is C10H18O. Right, so our molecular mass is the sum of the number of each species in this set times its mass. So we have 10 carbons. So we take 10 times 12, which is the molecular weight of carbon. We have 18 hydrogens. So we have 18 times the molecular mass of hydrogen, which is approximately 1. We have 1 oxygen with the molecular mass of 16. When I do this out, I end up with 154 grams per mole. Now I just need to convert my 10 grams of linalool to moles by taking the 10 grams of linalool. I can do this crosshatch method of unit conversion where I put the units so that they alternate, right? So I have 10 grams of linalool, 154 grams of linalool per mole, right? The grams are going to cancel out. I do out the math, and this gives me 0.065 moles of linalool. Now I have a way to determine, convert back and forth between mass and how many molecules. From how many molecules, when I undergo a chemical reaction, I can determine how many products, etc. I have. Right. So within reactions, we're going to consider several different classes of reactions. So the first one being reversible reactions. So these are cases where the products can go back and forth between the reactants, right? So we can start with linolyl acetate, and it reacts with water, and that forms linalool and acetate. But linalool and acetate also will react backwards to form linolyl acetate. So these are reversible because the reaction can go this way or it can go back this way. And we denote that by having these arrows that point in both directions. We can also have irreversible reactions. These are cases where once the products are made, they don't effectively go back. There's something that's stopping them. Either they so want to happen that once they go back, they're just not going to, once they happen, they're not going to effectively go back. So these are called irreversible reactions. So an example of that is tetrahydrocarbonic acid. And when it's exposed to heat, it forms tetrahydrocannabinol and CO2. Right? And so once the CO2 is generated, especially if it's released to the air, it's not going to go back. Right? So So these are two general types of chemical reactions: reversible, where the reactants and products can interchange back and forth; irreversible reactions, where the reactants can only turn into products and they can't go back. The other set we can think about is phase change or phase partitioning. So these aren't technically a chemical reaction, but we can write it as if it were a chemical reaction to help us in terms of keeping track and some bookkeeping. So we could have linalool, liquid solution. If I heat it up, I know it's liquid because in this case, I have a subscript with an L. It could vaporize, maybe in steam distillation and form a gas. If I cool that gas down, it will revert back to linalool. If I cool it down even farther, I could freeze it and make a solid linalool. So these subscripts with the parentheses are indicating of what phase they're in. We could also write this out as linalool in an aqueous solution or linalool in an organic solution, right? So think about linalool floating around in water or floating around in hexane. So um, this brings us to the question, if we leave linyl acetate in water forever, will it all become linalool? Right, so here's the linyl acetate. We break this bond via interactions with water, and we're left with the linalool and acetate. And the answer is no. We're going to have these reactions going back and forth and back and forth. So we can think about sort of these reactions in terms of pushing and pulling. So let's say we have A plus B goes to C plus D. There's what we call the forward reaction, right? So that's A and B forming C and D. And we also have the reverse reaction where C and D react to form A and B. We can have several different, right? So this is our reversible reaction. We can have several different cases. One, where this reaction rate forward is much faster than the reverse rate. In this case, if I have initially a lot of the reactants, over time that concentration decreases as the reactants are used up, the products are formed. We end up with many more products than reactants. Right, so this is considered a forward dominant reaction. The reaction is favored to the right. We can have the opposite, which is a where the reverse reaction dominates, where let's say we start out with uh, a large amount of C and D. It comes down, the reaction is pushed to the left. Or we can have, this dynamic state where we have, at equilibrium, or where these reactions are very even, and there's no change in the concentration with time. Okay, so even though we're at equilibrium, these reactions are always happening, but at equilibrium, the forward reaction and the back reaction are happening at the same rate. So there's effectively no change in concentration. Right? So we want to know in engineering these extraction systems several things. One is how fast things are going to move from left to right or right to left. And then at equilibrium, how much of the reactants and the products exist. We can do that with what's called equilibrium constants. And so we can quantify this using these equilibrium constants. So let's start with just a generic reaction. We'll just say A reacts to form B, and B can reversibly form A. Our reaction constant, K, is the ratio of the concentration of products over the concentration of reactants. Okay, and this is a constant at any temperature. So no matter how much A and B, we have K is always a single number at a single temperature. So let's do an example. Let's say we have a reaction equilibrium constant of 10, and we start out with 1 mole of A per liter. How much of B must there be if um, how much B must there be if it's at equilibrium? Well, I have K is 10, A concentration is 1 mole per liter, B concentration is what we want to find. I rearrange this and I find that my concentration of B is 10 moles per liter. This symbol here, I should have mentioned, these brackets denote concentration. So how many, usually written as moles per liter. This is so common, it's got its own name. We'll sometimes refer to this as molarity, and we can write this as a large capital M. Let's take an example in terms of extraction now. Let's say we have the compound A, which is sitting in water, and we want to transfer it to an oil. So this is, I have something in water, I expose it to oil. This compound A is going to partition or move between the water and the oil phases. We can have this partition equilibrium constant, K, and it is the ratio of, right, because we've written our equation this way, right, water going to oil, of products over reactants. Right? So this K, this partition coefficient, is going to tell us how much A prefers to be in the oil or the water. When K is greater than 1, A is going to preferentially move to the oil, versus if K is beneath 1, it's going to preferentially move into the water. Our functional groups and their polarities are going to give us an idea of whether these molecules want to be in water or oil. If we consider once again this A water going to A oil, these hydrocarbons, which are less polar, as we described earlier, are going to have Ks which are much, much larger than 1. They're going to want to be in the oil solvent. Conversely, if I have things like acids, right, they're highly polar, they like water, they're going to have Ks which are much, much less than 1, right? The equilibrium, the partitioning is going to want to push them into the water. All right, so one of the things that we often want to do is change the equilibrium. We want to move molecules from one location to another. So that we can, separate them. How can we change this equilibrium constant, right? Because I just said that, that at a specific temperature, that K cannot be changed. Let's consider a simple example of water, right? So water undergoing a phase change from liquid to the gas phase. And so my question is, what do we need to do to turn water from a liquid to a gas? Well, at a room temperature, that K is less than 1. It wants to be liquid. At 110 degrees C, right, above boiling, K is greater than 1. It wants to be a gas. Right? So we can see that temperature is going to control um, that equilibrium constant, right? So higher, as we change temperature, these numbers, these Ks are going to change. So temperature is going to be our method of altering these uh, Ks and therefore altering um, how we can partition or what species are present. Let's take a brief conceptual understanding of why temperature changes the equilibrium. Let's stick with, for example, uh, you know, water turning into water vapor. To do this, right, I need to put in heat, right? Think about turning on your stove. I'm putting energy into the liquid water to turn it into a water vapor. We call this an endothermic reaction. Endo meaning requiring or pulling in, and thermic, energy. Um, so we could really write this equation as liquid water plus heat goes to water vapor. If there's not enough heat, there's not enough to push this forward. When things are cold, you know, water vapor wants to go back to fill in that bucket of heat. Conversely, some reactions give off energy. These are called exothermic, exo meaning release or outwards. This would be a case of oxidation, so turning limonene into carbonone, CO2, water, and heat. Right? And so these tend to occur um, thermodynamically um, at colder temperatures, right? So if we have more heat, so higher temperatures, we push the reaction away from the heat, right? That heat is used up and we move to the other side. I don't expect you to really fully understand what I'm about to talk about is the little bit more mathy version. There's entire courses on this in chemical engineering as well as physical chemistry. Um, but just to give you a little bit of the math, our reaction equilibrium is controlled by this concept called free energy, which we mark as delta G, so the change in G, free energy. And this is equal to the change in the heat absorbed or released. So uh, delta H is positive when heat is pulled in and negative when heat is pushed out. And then I have this minus T delta S, and the H is enthalpy, S here is entropy, and this is a measure of disorder in the system. Um, uh, So our reactions tend to be favored when heat is released. So when delta H is negative and or the system becomes more disordered, so delta S is positive. I can directly relate this free energy term to our equilibrium constant by saying that K is equal to the exponential of negative delta G over RT, where R is the universal gas constant, which you can look up in the table. T is the temperature in Kelvin, not Celsius, and delta G is described up here. And these delta G's are often tabulated and you can look them up. All right, let's consider, now that we've sort of talked about chemical reactions in a very, very brief overview, let's consider the steam distillation of lavender. So this is what we have shown you before. We take the plant material, we chop it, we put it into our uh, uh, distillation chamber where we have heat, we have um, a tank of water. That water vaporizes. It comes up. It um, heats up the lavender. The lavender parts vaporize. We come up. We cool the vapor down, um, and we then collect our essential oils and our hydrosol. There are many different reactions which are all occurring at the same time, right? So there's water turning to steam, linalool acetate in the solid form, sitting within the trichomes, turning into linoleal acetate. We have linalool going into the gas phase. Uh, as it moves around, we have, of course, an exposure to steam, right? And we had said earlier that linoleal acetate reacts with steam to form linalool and acetic acid. Right? So we have all of these reactions which all occur simultaneously. And it's our job to try to manipulate the conditions of these systems to get out the compounds that we want. Okay, so remember, in this case, K is going to increase with temperature. Um, So the hotter the temperature, the more we're going to go to linalool and acetic acid. While linalool might be intriguing, acetic acid is vinegar, is the vinegar smell. So, right, we want to modify our temperatures and our conditions to try to maximize the presence of these nice lavender smelling compounds. So let's actually try to quantify some of this. Let's consider that we've gone through, we've collected our essential oil and the hydrosol. And we initially in that hydrosol have 1 mole per liter of linoleal acetate in that hydrosol. If our equilibrium constant is 0.02 and we've got all this extra water, some of this linoleal acetate is going to form linalool and acetic acid. So we want to know how much of this reaction, which is undesirable, is occurring. We're going to do this using what we can call an ICE table, initial, change, final. Here, and this is how we're going to approach all calculation of reaction extents. Up in this initial spot, we can write out how much of each species is there initially. So it tells us, the question asks us if we have 1 mole per liter of linoleal acetate, how much do we have initially? Well, 1 mole per liter. The concentration of water is about 64 molar, but that's not going to change. So we can just write that in there. If we have initially no linalool or acetic acid, we have 0 of each of these. I now look at the change. How many molecules of linoleal acetate react in this? In other words, what is the stoichiometry? Well, here it's 1, so I have some change, so minus 1 times x. We don't know how much is changing, but we know there will be a change. Same thing, x moles of water will react. And then on the product side, I'm going to gain moles. So I'm going to form linalool and acetic acid. So I have a plus x and plus x here. So at the end, I have, after we've reached equilibrium, I end up with 1 minus x moles of linoleal acetate, 64 moles of water, x moles of linalool, and x moles of acetic acid. Because there's essentially no change in these, in the concentration of water, these are generally eliminated from these calculations. So remember, we also say that the K, our equilibrium constant, is our products over reactants. That's 0.2. And so we can look over here. What's our reactants, right? Linalool and acetic acid. What's their concentration? X and X. So I have X times X. What's our reactants? What's the concentration of the reactants at the end? Well, it's 1 minus X. So that goes down here. I can take this piece, rearrange the equation, and I get x squared plus 0.2x minus 0.2 equals 0. And this gives me, if I use the quadratic equation, this tells me that 0.358 moles have reacted. Right? So anywhere that I had an x in my chart, I can go in, pop that in, and I can see that in the end, I'm left with 0.642 moles of linalool acetate. I have 0.358 molar linalool and 0.358 molar acetic acid. We can do the same thing um, for partitioning, right? So let's consider another example. Here we're going to consider limonene extracted by pressing oil peels. So let's say that we had 100 milligrams of limonene per liter of oil that's been extracted. If that final extract contains 0.5 liters of water and 0.5 liters of oil, and we have a partition constant of K is 10, how much limonene is in the oil and how much is in the water? Remember, right? K in this case is above 1, so that is going to indicate that we're going to move most of that limonene should end up in the oil, right? So that's at least in our mind where we should end up. So we first need to solve this problem. We need to know how many moles we have because all of these Ks require us to work in moles. So we can convert our limonene mass to moles using the molar mass of limonene. Here, this is, you can look it up or calculate it yourself. If I have 100 grams um, of limonene, there's 136.25 grams per mole. This leaves us with 0.734 moles of limonene. Right, we need our equation, right? So limonene goes from water to the oil and back and forth. We need our equilibrium, right? We have our partition coefficient. K is 10, right? Products over reactants. So here we have limonene concentration over the water set up, and then we're going to construct our ice table. Right? So here we have the species in water, in oil, will have initial, change, and final. Now, here's the thing. We don't know from the problem statement how much started out in the oil or in the water. That's completely okay. We can just assume that it's all in one or the other because at equilibrium, we don't care where we started, we only care where we ended up. So we're just things started in the water. So we had 0.734 moles of limonene. If it all started in water, that was 0.5 liters of water. I can do out this math. And this gives me 1.468 molar initial concentration. How much is moving from water to oil? We don't know. It's X. It's our variable that we need to solve for. So our final concentration is 1.468 minus X molar. In the oil, we have the same thing, but opposite. We started with no limonene, right? Because we assumed that everything was in the water. We have X, which is, that's how much is going to move to the oil, leaving a final concentration of X. So I can take my final concentrations, plug them into the partition equation. This gives us 10 equals the concentration of X. Sorry, X over 1 minus 468 minus X. I can solve this equation. And when I do, I find that X is 1.335. So I can plug that in. In the end, our water is 0.133 molar, and our oil concentration is 1.335 molar. Okay, so now we have the concentration of limonene in oil and water, but we need to figure out, right, how much is there, right? So what's the mass in there? Well, we can convert concentration to quantity, right? So the number of moles is concentration times volume. So the moles in water are the concentration, which is 0.133 molar times zero point 0.5 liters, right? That's the volume. And that gives us our final number of moles of 0.0665 moles. If I want to turn this into a mass, all I need to do is multiply the number of moles by the molar mass. In this case, 136.25 grams per mole, leaving me with 9.06 grams of the limonene in the water. I can do the same thing with the oil using the final oil concentration of 1.33 molar to give 0.665 moles or approximately 90 grams in the water. Okay, so if we think we started out with 100 grams, we ended up with most of those grams in the oil, just like we expected. Okay, so now that we've thought about this, we can see how um, we can partition uh, compounds from water to oil. We can look at how much compounds are going to react and change, and how these are going to form in equilibrium. As, like I said at the beginning of this lecture, we often want to modify this equilibrium. We want to change it to drive the um, partitioning to our desired products. So in order to do that, we have to disturb the system. We have to change something about it to make the reaction go more. So one possibility is to add more reactant, right? I could add more acetic acid, right? And if I added acetic acid, it would push the linalool back to linoleal acetate, right? So if we add A, it's going to shift, it's going to push that reaction forward. Conversely, I could remove the product, right? So in this case, um, if I'm thinking about uh, THCA decarboxylating to THC plus CO2, if I remove the CO2, right, the equilibrium will shift to the right. And then, of course, we can add heat or change the temperature to change that equilibrium constant to shift things left or right. If in this case we had A plus heat goes to B, if I increase the temperature, I add heat, I'm going to push the reaction to the right. Okay, so all of these things are ways that we can manipulate uh, our reaction and our system. This brings up a possibility. Let's consider that same limonene that we extracted by pressing the oil peels, right? We have extracted some of that limonene into the oil, but is there any way to get more of that limonene out of the water where it could react to form the undesirable acetic acid and into the safe oil? We could separate the oil and the water, right? Because they're they're different phases. You can carefully siphon off or decant the oil that's containing the limonene that we want and add another half liter of oil and mix, allow it to go to equilibrium again. So let's see what happens. Here was the initial set that we had before, right? So in the water from our previous partitioning, we had 0.133 molar limonene in the water. And we have now brand new fresh oil. So there's none in the oil. If I allow it to reach equilibrium, I have limonene, which is going to leave the water, move to the oil. So I have a change of minus X in the water plus X in the oil. This gives me a final concentration of 0.133 minus X molar in the water and X molar in the oil, just like before. I can set up my partition uh, equilibrium constant. So that was 10. And that equals our products, so the limonene and the oil over the reactants, so 0.133 minus X. So the amount of X that's changing is 0.12. If I put this into my table in at the end in my aqueous phase, my water phase, I have a final concentration of 0.013 molar, and in the oil I have 0.12 molar. We can again figure out what the mass is in the water versus the oil, just like we did before. So here's the math showing here. Um, and what you'll see is we end up with about 0.9 grams in the water and 8.1 grams in the oil. Sorry, that should be the oil. I want you to notice that in our first partitioning, we had a high concentration of the limonene in the oil, right? So 1.335 molar. After the second extraction, I have a much lower amount of um, limonene in the oil. So only 0.12 molar, so more than 10 times less. We can see that outcoming oil that we've now extracted is significantly lower in quantity, right? Because um, there was less to do that extraction from, but we have more recovered. So remember in that first few days of the class, we talked about a trade-off between quality and yield. So I've increased my yield, but at the end I have lower quality. Because of this, I might want to keep this oil and this oil separated, right? One I have a high quality oil and one I have a lower quality oil. But I have more out of the water. I've preserved that flavor, that smell. All right, this next thing that I want to talk about is that these complex molecules often can undergo multiple reactions at the same time, some of which are desirable and some of which are undesirable. We often write this as follows. A generic molecule goes to D, a desired product, and or A goes to an undesired product, U. For an example, if we take tetrahydrocannabinolic acid, we have both a desired and an undesired reaction that occurs. When I leave it out and exposed, it can decarboxylate to make cannabinol and CO2. This is what we want to happen. Or it can oxidize where it forms CO2, water, and other degradation products, right? So if this reaction occurs, that's great. This is the high value product. At the same time, if it reacts with oxygen, it's just forming unuseful products. So we want some of these, we want to control the situation as much as possible to drive um, the reactions that we want and minimize the reactions we don't want. So in this case, we would want to minimize exposure to oxygen during this decarboxylation reaction. But we want to, right, to minimize this undesired reaction. But we want to open up whatever container is containing this THCA to release the CO2 to drive this reaction forward. And when we do that release, we of course let air in, and so we're exposing the THCA to oxygen. Right? So we had this trade-off which is occurring. We can see this similarly in a solvent extraction of vanilla, right? So we want the vanillin, which is sitting either as a solid or liquid in our vanilla beans, to move into an ethanol solution. This can be relatively slow. So one thing that we could consider is heating that reaction to make it go faster, right? But when I heat it, not only is this desired reaction going to go faster, but we also can end up with undesired reactions where vanillin turns to uh, guaiacol, which is a smoky vanilla flavor, or if we let it go too long, we can form burnt notes, right? So we have desired things and undesired things, and so we can control um, the temperature in order to try to control how fast these two pieces occur. So even though we might want this to go faster by heating it up, we would have to pay a penalty in getting these off notes. So therefore, we often let this sit for a very long time at a lower temperature to maximize the vanillin extracted so that we don't form burnt products. Okay, so the last thing that I briefly want to talk about is reaction rates, right? So we just talked about, using heat to, lower temperatures to change how fast something is happening. Um, so this begs the question of how fast is something going to be converted? And we can say that A plus B going to C plus D, how fast this is happening is determined by the rate of this reaction. And we generally write this as the rate equals a lowercase k, which is our reaction rate constant, times the concentration of A times the concentration of B. This reaction constant K is once again going to have this exponential form, right? So K is some pre-exponential factor times exp to the negative EA. This is called our equilibrium constant, our reaction activation barrier divided by our gas constant over T. Don't worry too much about the details, but do notice that as I increase temperature, this whole term decreases. And because it's negative and the exponent of a negative becomes a small number, um, sorry, uh, becomes a negative is makes this a small number. By increasing the temperature, we decrease this term that makes this less, makes it closer to one and increases the rate, right? So the higher the temperature, the faster the rate. And so we have to balance um, increasing temperature to go faster, but not so fast that we end up getting undesired reactions. Okay, so we can think about, I just want to hone in the difference between equilibrium and rate. So equilibrium is where things end up at infinite time. So think about this. You're doing a car trip from one side of the country to the other. Equilibrium is where we end up, and rate is how fast we get there. And so we may end up going at a very slow rate. So we may end up never getting to equilibrium. And so with some of these undesired reactions, that's what we want. We want to go so slow that they don't end up actually happening. All right. So let's take all of this that we've talked about um, and put it in terms of extractions. All right. So um, we've talked about if I remove um, if I remove products, I can drive the reaction forward. So this is what happens in distillation, right? I have my um, lavender, I form a gas phase. I take that gas phase and I cool it down to form a liquid again, and that liquid is put in a separate location. So this now sees a lower vapor uh, concentration. It vaporizes, and we drive the reaction forward. If we're thinking in terms of extraction, right, I take my leaves, whatever the plant matter is, I put in some sort of solvent, I reach equilibrium. How do I drive it further along to equilibrium? Well, I can decant off that liquid, add um, fresh solvent, and now I reestablish equilibrium. If I have a gaseous product that's desirable, so right, if I want to turn THCA into THC and CO2, I can pull uh, some sort of vacuum to remove that CO2 from the system to drive this reaction forward. Conversely, if I didn't want this reaction to go forward, I could pump CO2 into the container and it would push the reaction backwards, right? So the idea when we're doing these extractions is we want to change somehow the system so that our equilibrium shifts so that we can move we can move compounds around. Okay. So my last comment with this, though, is our extraction is going to change, right? All these things are changing the molecules. We get uh, some things that are recovered, we get what we want. Some things get left behind. Um, so some things are not moved. This can either be desirable or undesirable. Some things are transformed, right? So THCA going to THC. We have some sort of change. This once again can be desired in terms of THCA going to THC or undesirable. Think vanillin going to off notes. But then we also get co-extraction. So, right, I can't say only the vanillin gets extracted. We often extract other things like chlorophyll that get removed. And these often give off colors or off smells. Okay, so everything that we're going to do with these changes in trying to drive the system and alter equilibrium are going to have effects on how much is recovered, but also what's left behind, what's co-extracted, and what's transformed. Okay, at the end of today, you should now have at least an idea of um, what drives changes and how we can quantify how much of a change happens. You should have a decent understanding of basic reaction notations. You should be able to calculate equilibrium extents. You should be able to evaluate how temperature alters equilibrium and how molecular structure relates to polarity, volatility, and partitioning. I know this covered a lot of chemistry in a short period of time. I'm going to link to one of a colleague's videos that will go more in depth if you want to learn more about uh, here a more in-depth general overview of basic chemistry. Okay, for next time, we're going to start taking these concepts and fundamentals that we've been talking about and putting them into uh, an actual extraction system and start thinking about the engineering. So at the end of this module 3, you should know how we can name plants and how they plant molecules and how they behave. And then, of course, today we've talked about how we determine how much of change happens. All right, I'll see you next time, and we'll start talking about system level thinking and the engineering behind extraction technologies.